Okay, so now that we've had the opportunity to get familiar with the normal distribution, to get familiar with the standard normal distribution and the tables that are available, we're now going to try and make use of the powerful nature of the calculators which we use as we study applied maths. I'm going to talk you through how you can make use of your calculator to also come up with those same results we will use in the tables to produce. So, a normal distribution has two parameters, the mean, mu, and the standard deviation, sigma. And if I wanted to find the probability between 2 points, A and B, between two values, A and B, I could sketch a diagram and I'll be looking for this shaded area. The syntax on your calculator to calculate that shaded area, to calculate that probability, is as follows. We're going to use the normal cumulative distribution function. It will be NCD on your calculators, and I'll refer to it as NCD, followed by the minimum value we're interested in, comma, the maximum value we're interested in, comma, standard deviation, comma, the mean. If you notice here, the standard deviation and the mean are the opposite way round to how we usually write a distribution, so be really careful when it comes to working with these. You can find the function we're talking about in the menu system by first going to options and then the statistics button and then distributions, and from the distribution list you want to choose normal cumulative distribution, so the NCD. Okay, so let's do an example with numbers, and you probably should bring out your calculator at this point so you can punch in the values and get the same result as I got. So if we're looking at a normal distribution with a mean of 30 and a standard deviation of 4, and I want to find the probability that x is less than 33, firstly, as always, we want to draw a diagram so we make sure we're picking out the right region from our distribution. As we draw the diagram, what is the lowest and the highest limit? We don't actually know, and the normal distribution is asymptotic, meaning it doesn't actually cross the x-axis, so it goes on forever towards negative infinity and forever towards positive infinity. So I do know where 33 is, but what is the leftmost value? Well, it's negative infinity, but I don't really want to have to put in negative infinity. Instead, I just need a really extremely small number, and negative 1,000, negative 10,000, negative 1,000,000 if you want will do in this case. It's far away enough that I will get the correct result. If you remember, 99.7% of the data of the values are within 3 standard deviations. So as long as I'm more than 3 or 4, or even just to be safe 5 standard deviations away, that value would work. I recommend just blanket use negative 1,000 or negative 10,000 or whichever number you prefer. So my minimum value is going to be negative 1,000. My maximum value of the shaded area is 33, standard deviation of 4, mean of 30. Press enter or execute on your calculator and it should give you your answer to multiple decimal places, but as usual I'm going to round to 4 decimal places and we get 0.7734. Okay, so that was the syntax: minimum, maximum, standard deviation, and the mean. The diagram makes sure we're actually pulling out the correct values to put in place here. Making sure we write our distribution with standard deviation squared in the first place also helps to make sure we put the right values into the calculator. Let's try another one. The probability that x is greater than or equal to 24. Okay, so let's do a diagram. I know the mean is the middle value, so that's going to be 30. I'm also just going to set my right tail as 1,000 and my left tail as negative 1,000. Any suitably extremely positive or extremely negative value will do in these situations once again. Okay, so greater than or equal to 24 is this shaded area. Can you pick out the minimum and the maximum? So in the calculator, the syntax calls for 24, 1,000, 4, and 30 to be plugged in. Press enter on your calculator, and that's going to spit out your answer once again, 0.9332. Okay, hopefully you're getting the hang of this. The diagram's still important. The calculator seems like a shortcut, but it's only a shortcut if you actually know what you're doing. Otherwise, it's just a lucky guess. So that's why I've made sure you learn how to standardize first, and now we can make use of the calculator because we know what we're doing. Okay, let's look at this one. We're not actually going to the tails in any of these values necessary. So the probability that it's in between 33.5 and 38.2. So 33.5, 38.2, I'd expect them both to be on the right hand side since they're bigger than 30. I'm looking for this little sliver of shaded area right here. The minimum and the maximum, as you can guess, 33.5, 38.2, followed by the standard deviation and the mean. Enter 0.1706. Okay, just as fast as that, just as speedy, just as thorough. I've written down the probability statement, I demonstrated it on a diagram, plugged it into the calculator, wrote down my answer. The examiner wants to see all of this, and to be honest, more importantly, I want to see all of this. A diagram for each question and a sensible method in your calculator. Okay, let's get a little bit more tricky. What if I was asked for the probability that x is less than 27 or x is greater than 32? Let's start with a diagram. These should be coming out second nature to you. I hope those diagrams are improving and you're getting quite a smooth normal distribution curve. Sensible size, it doesn't need to be massive and it definitely doesn't need to be minuscule, just a sensible size for you to work on. Less than 27 is this shaded area in the left tail, greater than 32 over here in the right tail. I can find each of those areas individually and separately and add them together. And potentially that might be the default way that you would do this. And let's see what answer we get. I'm just going to speed through this for you. If you didn't know, you can actually use the cumulative function and then press plus and then plug in the cumulative function again. So we're actually adding these two separate cumulative functions together to answer our question. Okay, so that gets us 0.5352. But I'm wondering if you spotted a different approach. Here we found the shaded area, which was two separate areas, so two separate calculations. But what about this void space in the middle? What about this unshaded area? Well, actually, I know that the whole area underneath the curve equals 1. And if I actually subtracted that middle section, that unshaded area, that would leave me with the two bits on the outside. That would leave me with the tails. And hopefully that would give me the same answer. So how about I shade this purple and we're going to do 1 minus the purple area. So it's 1 minus NCD 24, 32, 4 and 30. Okay, so that's going to be the purple area that I'm subtracting. I want you to be on the lookout for smart things like this that you could potentially do, which you wouldn't really notice, once again, if you didn't have the diagram. And I keep emphasizing this because I know that the harder exam questions really rely on students who can model the situation well, and the diagram is actually your first step of being able to model and represent exactly what's happening in front of you. If we do our 1 minus, we do end up with exactly the same answer the second way round. Okay, so let's take a look at a slightly more advanced question, and this is going to be not just a normal distribution. It's going to give you an opportunity to work with some topics you've seen before. So stay alert and see if you can notice when there's an opportunity to employ some of those previous topics. So we're looking at the distribution of IQs of adults, and the classification for a genius is that somebody has an IQ above 140. So let's see if we can find the probability that an adult chosen at random is a genius. So the probability that X is greater than 140. So we're going to go ahead and set out the statement, and we're going to use the syntax that we've been using all day so far to find the probability that somebody is a genius. This bit shouldn't take you more than 15 seconds really. Just punch those numbers into the calculator, hit enter, and we get 0.00383. Now, you know I'm a big fan of 4 decimal places, but we have so many leading zeros here that we probably lose some accuracy by going for 4 decimal places. So 3 significant figures seem sensible, and that's what the question asked for anyway. Okay, so in part B, we're told that 20 adults take this test. What is the probability that 2 or more of them are geniuses? Well, here it is. There were 20 adults taking the test. That's 20 trials. We actually have a binomial distribution where n is 20 and p is the probability of being a genius. Okay, so from there, I have a binomial distribution where I can work out the expectation. Expectation is n times p, and it's actually 0.0766. It's a really small expectation. But we're looking for the probability that x, or in this case y, is greater than or equal to 2. The probability that there were 2 or more geniuses in this room of 20 adults. Well, here's my diagram. It's not that accurate. It will be quite difficult to show the immense skew that this diagram really has. But it does what it's meant to do. It lets me know that I'm looking in this right tail, and what is that probability over there? The probability that is greater than or equal to 2. Well, we're doing a binomial distribution now, a binomial cumulative distribution function calculation, and we put in our numbers again, the minimum, maximum, n value, p value, press enter, and there we go. Probability is 0.00266, once again to 3 significant figures. Alright, so normal distribution question to begin with, but we had to spot that opportunity to use the binomial distribution afterwards. We knew there was a specific number of trials, and in this case the trial was an adult that is tested to see what their IQ is, and there were 20 adults tested to see what their IQ is, so there were 20 trials, 20 attempts, and that is exactly the criteria we look for in the binomial distribution. Alright, so I'm going to leave you to try some problem solving involving the normal distribution, but just keep your wits about you, keep your smarts up, and really be alert to whether or not it deviates away from a normal distribution question. The examiner isn't just going to give us the straightforward questions. Maybe they will for part A, and maybe even part B, but C, D, E, and F are really checking to see that you're paying attention and you know your stuff.